In 1905, with Einstein's theory of relativity, the secret of the universe's birth was finally revealed. Whether he intended it or not, it was discovered that the universe has a beginning. That beginning was so mysterious that we could hardly imagine it. But having a beginning also means there must be an end. Just as humans have a lifespan, celestial bodies like the Earth and the Sun also have lifespans. This implies that the universe that contains them also has a lifespan. When humans reach the end of their lifespan, they can no longer engage in life activities or move. Celestial bodies, when their end approaches, meet a dramatic death in forms such as black holes or explosions. So, what kind of end will the universe, a far more colossal entity, face? Today, from the comfort of our room, let's explore the science topic. How will our universe end? Let's begin right now. In 1915, Einstein published the great theory that explains the laws of the entire universe, the general theory of relativity. As a result, this beautiful equation, the Einstein equation, plays a crucial role in explaining the story of the universe. This equation describes how space bends when matter or energy exists within it. In other words, it can be considered a comprehensive summary that contains everything about general relativity. Within it are terms like the Riemann tensor, Ricci tensor, and energy momentum tensor, filled with unknowns that are difficult for the general public to even conceptualize. But if these unknowns could be simplified or their exact values known, only then could we come closer to the truth of this universe, the foundation of everything. However, the problem was that even Einstein, who presented this beautiful equation to the world, could not find its solution. The reason was not only the human aspect of Einstein being relatively weak in mathematics, but also because the equation itself had a monstrous level of difficulty. The Einstein equation goes beyond equations with one or two unknowns like the first order or second order equations we commonly encounter, and contains as many as 16 unknowns in a single equation, making it exponentially more challenging than typical equations. Moreover, this equation is not comprised of simple addition and subtraction that we learn in school, but is interwoven with numerous mathematical concepts such as differentiation and integration, making it nearly impossible to solve without being deeply versed in mathematics. Even after more than 100 years since the birth of this equation, the method to solve such equations has not been particularly clarified. And the best we can do is to substitute all possible values using supercomputers with extremely fast computation speeds. Therefore, even Einstein, who created this beautiful equation, could not solve his own equation, to the point where he worried about whether it could actually be used in real research. However, humanity proved to be more remarkable than expected. After Einstein's announcement of the general theory of relativity, scientists, shocked by the fresh insight, devoted themselves endlessly to solving the Einstein equation to uncover the secrets of the universe. By combining and dismantling this complex formula in various ways, they finally reached the first solution of the Einstein equation. And surprisingly, it took only 1 year. In 1916, just 1 year after Einstein's announcement of the general theory of relativity, German physicist Schwarzschild, who was serving as a soldier during the war with bombs flying overhead, attempted to solve Einstein's equation in a somewhat simplified manner. Since it was practically impossible to solve for the values of the 16 unknowns, he assumed a specific situation where all these unknowns would cancel each other out. Through this solution, he predicted black holes and calculated the size at which an object with a certain mass would become a black hole, or the size of the black hole itself, leading advancements in cosmology. However, this was solved under very specific conditions, and the equation still held many secrets. Therefore, in 1922, Soviet physicist Alexander Friedmann assumed that the universe has no specific direction or difference in matter density on a very large scale. In other words, the universe is homogeneous everywhere, and he decided to solve the equation based on this assumption. After complex calculations, Friedmann finally produced what is known as the Friedmann equation, which determines the shape of the universe. The Friedmann equation talks about how the universe evolves based on its initial conditions, and Friedmann thought of the universe's initial condition as its density. If the mass in a certain space exceeds the critical point, the gravitational force between the matter will be stronger than the force of the universe's expansion, leading to a contracting universe. Conversely, if the mass in a certain space is less than the critical point, the force of the universe's expansion will be stronger than the gravitational force between the matter, leading to an ever-expanding universe. And if the two forces are balanced, it would result in a flat universe. Simply put, depending on the current density of the universe that we actually observe, we can know how the universe is currently unfolding and what its eventual fate will be. Currently, the average energy density of the universe, including dark energy, dark matter, and all atoms, is approximately 10^1029 GCMNE3, which is a very sparse density, equivalent to about 0.3 onions in a cubic meter, compared to the density of stars or our bodies, which is about 1 grams cm3. It is an extremely low level. Now that we have the ability to measure the current density of the universe, we can predict how this universe will evolve in the future. So, what will happen to our universe? After Einstein's publication of the general theory of relativity in 1915 and Edwin Hubble's observational evidence of the expanding universe in 1929, the prevailing cosmological model among scientists was the steady-state theory. Of course, 2 years before Hubble, Lemaitre had proposed the Big Bang theory, but the idea that this vast universe originated from a single point with an explosive expansion was difficult for scientists of that time to accept. Nonetheless, since Hubble's observations provided evidence that the universe was indeed expanding, they had to acknowledge this fact. As a result, the steady-state theory, which simply acknowledged that the universe was expanding while maintaining that it was otherwise unchanging, emerged as the dominant cosmological model, replacing Einstein's static universe model. From today's perspective, the steady-state theory had many peculiarities. It couldn't precisely explain why the universe was expanding and merely stated that the universe was expanding for no apparent reason. Additionally, it made the absurd claim that atoms spontaneously appeared in the expanding space, which violated the law of conservation of energy. It might seem astonishing that the intellectuals of that time would entertain such implausible ideas, but the scientists who first heard about the Big Bang theory likely had similar thoughts. They must have questioned how the universe could have expanded from a single point. However, as time passed, scientific technology advanced, and astronomical data accumulated, leading us to accept the Big Bang theory instead of the steady-state theory. Consequently, we now have different thoughts about the end of the universe. This new understanding began with the story of the universe proposed by Friedmann in 1922, known as the Friedmann equations. According to the Friedmann equations, our universe could take on 3 possible forms. The first form occurs when the mass within a specific space exceeds a critical threshold, causing the gravitational force between the matter to become stronger than the force driving the expansion of the universe. If we could observe our universe from the outside, it would appear spherical. The surface area of the sphere is finite and determined by its radius, but because a sphere has no edges or corners, there is no end point. In other words, no matter how far we travel from a starting point, we would never see an end. Yet the space we can move through, the universe, is finite. This type of universe is called a closed universe. The second form occurs when the mass within a specific space is below the critical threshold, causing the force driving the expansion of the universe to be stronger than the gravitational force between the matter. In this scenario, the universe takes on the shape of a saddle, opposite to the spherical shape. This form of the universe has no end, and thus it is called an open universe. The third form occurs when the gravitational force between the matter and the force driving the expansion of the universe are roughly balanced. In this case, the universe is also an open universe, but it appears relatively flat compared to the saddle shape. Based on these forms, the fate of the universe is determined. First, let's discuss the closed universe. As mentioned earlier, a closed universe is a scenario where the gravitational force between matter is stronger than the force of expansion. In other words, the force trying to contract the universe is greater than the force trying to expand it. As the universe keeps expanding, at some point, the force of expansion and the gravitational force due to the total mass of the universe will reach equilibrium. Once this brief moment passes, the universe will start contracting instead of expanding. As a result, the distances between celestial bodies will gradually decrease. As these distances decrease, the gravitational forces between these bodies will increase, leading to a faster contraction. Thus, the previously expanding universe will now experience accelerated contraction. If the universe is indeed closed and we are alive until the end of the universe, the event known as the Big Crunch, we would experience an unprecedented hellish condition. Initially, the cosmic microwave background radiation, which exists at 2.725 K Kelvin throughout the universe, will increase in temperature as the universe contracts and its density rises. The temperature will increase proportionally to the degree of contraction. If the universe shrinks to 1/1000th of its current size, the temperature of the universe would reach 200 degrees, which is about half the temperature of the sun's surface. If we could witness this from Earth, we would see an amazing sight where the entire sky glows as brightly as the sun. As the universe continues to contract to ones of its current size, all the stars in the universe would explode, unable to withstand the extreme temperatures. When the universe contracts to 1 billion of its current size, the temperature would soar to 1 billion K Kelvin, surpassing the 900 million K that existed 3 minutes and 46 seconds after the Big Bang. At this stage, all celestial bodies, previously destroyed into atomic forms, would now be broken down into protons and neutrons. The universe would return to a state similar to the time right after the Big Bang when nothing existed. As the universe contracts further, it would reach a state similar to the early moments of the Big Bang. Protons and neutrons, now significantly smaller, would further break down into quarks and leptons. The universe would resemble the initial state of the Big Bang, with positrons, electrons, neutrinos, and photons. Finally, the universe would experience another massive explosion, similar to the Big Bang. This scenario is known as the Big Crunch. Some scholars propose a slightly different theory. Russian astronomer George Gamow, who developed the Big Bang theory by expanding on Hubble's theory of an expanding universe, suggested the Big Bounce theory. According to this theory, the universe contracts to a state similar to the early Big Bang, but never reaches the singularity. Instead, it explodes again, just before reaching the singularity. In simple terms, while both scenarios involve the universe expanding and contracting, the Big Crunch suggests that one universe contracts completely, leading to the birth of a new universe. In contrast, the Big Bounce suggests that the same universe goes through cycles of expansion and contraction. Though there's no way to prove it, if our universe were a closed universe, it would mean there is no true end, just a continuous cycle. However, recent research indicates that the possibility of our universe being closed is almost zero. If the universe were closed, its expansion rate would gradually slow down. However, observations of type Ia supernovae, which serve as cosmic markers, show that the universe is actually accelerating in its expansion. As a result, scientists are now exploring other forms of the universe to determine its ultimate fate. Next, the second open universe scenario occurs when the force of the universe's expansion is stronger than the gravitational force between matter. In other words, the universe's expansion is overwhelmingly strong, causing the universe to continue expanding indefinitely. Unlike the processes in a closed universe, the opposite happens here. As the universe continues to expand, its density becomes infinitely small, and unlike the closed universe, the temperature of the universe, which was at 2.725 K, starts to decrease. As a long time passes, the universe expands to the point where you cannot find any celestial bodies in the sky other than yourself, and the universe is on the verge of absolute zero K. The last stars burn out all the remaining hydrogen and helium, eventually extinguishing and transforming into one of the forms: neutron stars, white dwarfs, or black holes. Black holes begin to engulf other celestial bodies along with any remaining gas and dust. And after a nearly eternal time of 100 years, black holes evaporate through Hawking radiation, and the fundamental particles that make up matter, protons and neutrons, also decay. Although some remaining particles and radiation still exist in the universe, they too quickly disperse due to the immense expansion speed, effectively leaving the universe empty. At this point, the universe, where no celestial bodies exist or can be created, is practically dead. We call this scenario the Big Freeze. The Big Freeze theory is currently the most widely supported end of the universe scenario. Based on evidence of the universe's accelerating expansion, it is believed that our universe is an open universe and will face thermal death. However, experiencing the Big Freeze firsthand would require an immense amount of time. To reach this state, the universe would need to be at a point where no celestial bodies can be found beyond our Earth. Even 7.8 billion years from now, it is certain that many stars will still be present in our universe. Even if we find a way to settle on a new planet beyond Earth or develop technology to survive in the universe, we cannot prevent the thermal death of the universe, the Big Freeze. Just thinking about it is terrifying. But in an open universe, something even more severe could happen. This is the Big Rip, where all particles in the universe, even space-time itself, are torn apart. The Big Freeze hypothesizes that as the universe continues to expand, the distance between celestial bodies increases, preventing new stars from forming and eventually returning all particles to their primordial state. But what if the expansion speed of the universe becomes much faster than the Big Freeze? To put it simply, imagine pulling a common orange rubber band. Initially, the rubber band stretches as much as you pull it. But if you keep pulling beyond its limit, tiny gaps form, and eventually it snaps. Similarly, our universe would expand initially, but once it surpasses a certain limit, even space itself would tear apart. This Big Rip depends on the properties of dark energy, which are still not fully understood. Dark energy makes up about 69% of our universe, a substantial amount. As the universe expands, the density of ordinary matter and dark matter decreases faster than the density of dark energy. As a result, the force of dark energy driving the universe's expansion becomes stronger than the contribution of dark matter to the universe's contraction. Moreover, when the universe's size doubles, the density of dark energy remains almost unchanged. If dark energy is indeed driving the expansion of our universe will expand exponentially with time, reaching incredibly high speeds. As the expansion speed continues to increase, it will surpass the point where the universe can maintain its structure, leading to a future where everything, including Earth, the Sun, atoms, protons, and electrons, is torn apart. It would be the most catastrophic and brutal end among the possible fates of our universe. Fortunately, we have yet to prove that dark energy is causing the universe's expansion, and the idea that our universe will reach such a rapid expansion speed remains speculative. However, humans have always evolved by making the seemingly impossible possible. 4 million years ago, no one could have predicted that the human species would dominate this Earth. Therefore, as we wait for the universe's end, which is tens of billions, if not hundreds of billions, of years away, humanity will undoubtedly find a way to overcome this crisis. This has been a segment of Armchair Science.